Hey guys, welcome back to Life at Home Chemistry Shorts. Today we're going to be learning about bond length. We will look at the traditional potential energy graph that you see that represents bond length, and at the end we'll have an Excel challenge to help you with the concept and to give you some practice with graphing in Excel. There's a link to a PDF version of the challenge in the description below. Please remember to like and subscribe. It really helps as I'm trying to grow this channel. All right, let's go ahead and get started. So let's take a look at this graph that you often see. This graph represents potential energy of two atoms that are coming together to form a bond versus the bond length in angstroms. Remember that atoms are not rigid spheres, but mostly empty space occupied by moving electrons. Because of this, their electron clouds can overlap. This graph uses the potential energy of two non-interacting atoms as the starting point and calls it zero. As a bond forms, energy is released, so the potential energy goes down. The negative potential energy is relative to the atoms not interacting at all. Okay, as the two atoms come closer, nothing really happens until the atoms are close enough to start forming a bond. As the bond starts to form, energy is released and the overall potential energy goes down. The atoms continue to get closer as the bond forms because there is an attraction between the electron clouds and the other atom's nucleus. And of course, more energy is released and the potential energy continues to go down. Energy will continue to be released as the atoms get closer together. Notice the overlap in the electron orbitals. At some point, pushing the atoms closer together would require energy to be added. This is because of the repulsion of the two nuclei and the overlapping electron orbitals. Okay, a good illustration for the balance of attractive and repulsive forces is an interaction you may have with a friend in the hallway at school. As you see each other, you're drawn closer together so you can talk and interact. As you get closer, you'll find a distance that allows you to interact without being too close. If someone bumps you closer together, the immediate response is to step back.
Hello, Aaron. So how long are you folks in town?
3 more days, and then we're off to Paris.
Wow.
We're going with the Select Charter Group.
I love France. I was just there last year. In fact, I still have an envelope full of French francs.
Most of us have a bubble that we do not want people to invade. The bond length will be the point where the potential energy is the lowest, which is also where attractive forces are equal to repulsive forces. The attraction of the electron orbitals to the other nucleus is balanced by the repulsion of the two nuclei and overlapping orbitals. One other note, even when bonded, atoms will vibrate. As they continue to vibrate, they will get closer and further apart. The bond length is the average distance, but that distance is not completely constant. Okay, over in Excel, we have some data that I have taken off of Spartan Student software, and we've got bond length. We got various bond lengths in angstroms here. And then we also have relative potential energy for nitrogen, oxygen, and hydrogen with respect to those bond lengths. So what we've done is we've got a series of data points, and I'm going to do hydrogen to show you kind of an example of how the challenge works, and you guys can do the others to practice. So we're going to select our data here. We're going to go to Insert Scatter Chart, and you can see that this chart looks kind of similar to what you have already seen. And if you want, we can go ahead and add a couple of axis titles to this so that it makes more sense. And down here I can add and if I want to insert this character, I can do insert symbol, and I can add my little angstrom symbol there. All right, and on this side, oops, we can put okay, if I can get that right. And of course, you can make this thing look nice by fixing your title and doing all that stuff later. I just want to show you the basics of how to get this started. Now, with any set of data points like this, if we wanted to actually find the bond length, which would be the point where this graph is actually the lowest, most likely none of our data points are actually going to hit that spot. It would be a very coincidental thing if one of your data points were to actually hit the exact spot where this curve is the lowest. So typically what you're going to do is you're going to find some kind of mathematical representation of this curve, and then you're going to use that to mathematically calculate where your lowest point is. Or you could, I guess, draw the curve out and try to estimate it using the graph. But to be more exact, we want to do it mathematically. So now if we try to do this entire curve mathematically, what you're going to find is this is not simple math. This is not going to be very easy to do. So what we typically do in this particular case is we can approximate the curve here at the bottom by using just a standard polynomial. So what that means is I want to take these three data points that make up this lower little dip in this curve, and I'm going to graph them separately. So I know that this is going to be these three data points here, because you can tell they're one, you got the first one, and you got 2, 3, 4. So we'll skip the first one, 2, 3, 4. That's my lowest three. And then I'm going to insert a scatter chart with just these three. Now, once I've got this scatter chart, I'm going to right click on my data. I'm going to go add trend line, and you'll see your trend line stuff comes up. Now in this particular case, we're going to approximate this with a polynomial. So we're going to click on polynomial, and second order is good. And then we want to display our equation and our R squared value. I'll put these over here where we can see them better. And then I'll also go to here. I'll make these bold and maybe make them a little bit larger so you can get a good look at these. Okay. So now I'm not labeled this graph, so it's not very pretty. It'd be better to label this if you wanted to use this. But you can see that I was able to get a polynomial approximation of this little section of the curve. Now this is obviously, I'm going to move this over so you can see it better. This is obviously not going to work for this entire curve. It's going to just come straight down, dip here, and go back up. But for this little section down here, it is a close enough approximation that you can use this to calculate the actual minimum point in the curve. Now, if you've had calculus, maybe you have not, you will remember that the best way to do this is you want to find where the slope of this curve is equal to 0. You know, the slope will follow this curve, and then it'll be flat and equal 0 at the very bottom of this curve. And the way you find that is you want to take this and take the derivative of this. And we'll hop over and I'll show you mathematically how to do that. If you remember how to take a derivative and how we can solve and get the minimal point of this curve. And you can take this information and you can use this, and you can do the nitrogen and the oxygen, so you can have all three of these. And that'll give you some good practice for being able to analyze this type of data. Okay, let's hop back over here and do this calculation. I went ahead and pulled my graph over here so you can see it. So here is my equation. And if I want to take this equation, I want to take the derivative of this. And if you guys remember, I can take the derivative by I multiply my exponent times the coefficient that's in front of the x. And in this particular case, you would assume that's kind of like x sub 0 because it's like a 1. And so basically this will cancel out. And then of course you're going to get 2 times 1,396.5. So that's going to be 2,793. And then we lower that to an x minus 2186.8. And this is the derivative of the line equation that or the polynomial equation that for our approximation line. And this is also going to give us the slope. Now we want to know when that slope is 0. So when that slope is basically flat along the bottom of this line, you know, the slope at any point is going to kind of follow this curve, and when it's flat, we'll know it's at the minimum. So we want to say that this is equal to 0. And if I solve that, 2793x equals 2186.8. And of course, then you divide. And so my x is going to be equal to 0.78. And we know our units is angstroms. And if you remember, if you look back at the curve that we had earlier, the closest data point we had was 0.8 angstroms. So our data point wasn't exactly at the minimum. So that's why you have to do some sort of mathematical approximation and actually get the minimum, because rarely in any situation are you going to have a data point that fits exactly where you want it. So it's a good practice to be able to find a mathematical representation and be able to solve for whatever point that you want. Okay, check out the link below and you can download a PDF version of this Excel challenge. You can go ahead and complete the nitrogen and the oxygen version, or the nitrogen and the oxygen data as well, to give you some practice and to let you see kind of how this works. And hopefully this will be clear enough you'll be able to follow it and figure out what's going on. Okay, I hope you found this to be helpful and that you have a better understanding of bond length as well as graphing and trend lines in Excel. If you like this video, hit the like button and don't forget to subscribe. I hope to see all of you young chemists in training again soon.